Black math! Give me some math and I'll give you some flack. Black math!
Saxon was kind of reamed for not having a geometry curriculum. So they developed this within the last 15 years. They developed this geometry Saxon, and because they claim that if you do all three of their algebras, algebra 1, 2, and advanced math, then you don't need geometry because there's enough geometry in those curriculums. So basically, you've had a lot of the geometry that we talk about in this book, but this is, so you can get a credit for it. So a lot of this is going to be review, but we're going to talk about solids and what's happening there. So
I learned this before.
You've learned it before.
I didn't ask you to change it.
Wow. All right. Sorry. Are you thinking it though?
No.
Okay.
I try and block out algebra 2.
So let's just do a quick review. The three-dimensional figures called solids. Solids can have flat or curved surfaces. Okay, the surfaces of some solids are polygons. Any closed three-dimensional figure formed by 4 or more polygons that intersects only at their edges is called a polyhedron. Okay, so like a box, this is a polyhedron. It's also called a prism because it is the same shape all the way up. But if you think about like the pyramids in Egypt, that's not a prism. It's not the same shape. Well, it is the same shape. It just gets smaller and smaller all the way up to the point, right? But a prism has the same shape all the way up. But that would be considered a polyhedron. They're both polyhedrons, but a pyramid is only a polyhedron. But it basically has all these polygons that connect, all right? And there's no circles or anything weird like that. Some other solids have circular bases or curved sides. A cone is a three-dimensional figure with a circular base and a curved lateral surface area that comes to a point. A cylinder is a three-dimensional figure with 2 parallel circular bases, the top and bottom, and a curved lateral surface that connects the bases. A sphere is a set of points in space that are fixed distance from a given point. That's how they define a sphere. It's in space, the set of points that are a certain distance away from the center. Think about it. Like on a circle, the circle is the set of points two-dimensionally that are the same distance from that center. But a sphere is all those plus the ones out here and all the way around. So it's just a set of points. A sphere is just a set of points in space that are the same distance from a center, from a given point, a center. Okay, so let's just do a quick sketch of what these guys look like. So this is a polyhedron. It's not a cube. Okay, here is a cone. Here is a cylinder. Here's a sphere, and usually what we do for sphere is we kind of do something like that. Okay, so in your homework, you're going to have to classify each of these type of things. So it's going to give you, is this a polyhedron, a cone, a cylinder, or a sphere? Okay, so let's do that. We're going to share a screen here.
So cone, I guess I could draw right these.
All right, so let's classify this. So what is this? What is A? Is that a cylinder? That's a cylinder. It's just on its side, so it's not anything weird. So here's why it's a cylinder. The figure has 2 parallel circular bases, okay, and a curved lateral surface area. What happens if you unwrap that lateral surface area? What happens if you unwrap that? What shape is that? If you take the label off, it's a perfect rectangle, okay? So that's why when you're trying to find the area, the lateral surface area, unwrap the label off of that can of beans, okay? It's a rectangle. What's the length of the rectangle? That's the distance around the cylinder or the circumference. And the height is just the height of the cylinder, okay? All right, what about this? What is this sucker? B. Polyhedron. And more specifically, it is a prism because it's that same triangle all the way up, right? So this says the figure is made up of 5 polygons that meet at their edges. Therefore, the figure is a polyhedron. What about this? That's a cone. It looks like an ice cream cone. Figure has a circular base and a curved lateral surface that comes to a point. The key word here, or key phrase, is it comes to a point. Okay? Therefore, the figure is a cone. Good job. All right. Moving on. So each flat surface of a polyhedron is called the face of the polyhedron. So the face of a polyhedron is the flat surface. Okay, so how many faces does this polyhedron have?
3. 1.
Only 3 that you can see,
Oh, that's
6.
nothing.
Right? So remember, there's some on the bottom too, and in the back. So you got front, back, left, right, top, bottom. So with a rectangular prism, it's always pairs, right? The top and the bottom are the same. The left and the right are the same. The front and the back are the same. So this is 6 faces right up here. 6 faces. Okay. The vertex. So the segment that that is the intersection of the 2 faces called the edge of the polyhedron. Okay, so the edge is the segment that intersects 2 faces. Intersecting 2 faces. Okay, how many edges does the rectangular prism have?
Oh, it's quite, oh, without, oh, that's a lot.
How many edges?
12 feet.
So I see one here, one here, one here, one here. Basically, how many lines are you drawing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 edges. Good. All right, and then the last one is the vertex. A vertex of a 3-dimensional figure, it doesn't have to even be a polyhedron, is the point of intersection of 3 or more faces of a figure. So the vertex is the point of intersection of 3 or more edges or faces, basically. So it's got to be 3 or more. So never is there just one point that doesn't touch at least 3 faces. So how many vertices does this have? How many vertices does that rectangular prism have? 8. Look. 1, you're just looking at the corners now, not the edges. 1, 2, 3, 4, 5, 6, 7, 8. So 8 vertices. Okay? All right, so a prism is a polyhedron formed by 2 parallel congruent polygonal bases connected by lateral faces that are parallelograms. Okay, so a prism, this is also a review. We've talked about prisms. Prism is a polyhedron formed by 2 parallel and congruent bases. So polyhedron formed by two parallel and congruent polygonal bases. It's got to be polygonal. So it's a cylinder. It's technically they're two congruent bases. They're both circles on the top and the bottom, right? But it's not a polygon. So by two parallel and congruent polygonal bases, okay, and then their sides have to be parallelograms, and they are. If you have two congruent parallel bases, then their sides are going to be parallelograms, okay? And their lateral faces are parallelograms, okay? Okay, this is another word that you need to know, bases. Those are the two polygonal congruent parallel faces. Usually you find them on the base, the top and the bottom, okay? But sometimes they're side by side or whatever. So a pyramid, this is another polyhedron, pyramid, as opposed to a cone. A pyramid is a polyhedron formed by a polygonal base and triangular lateral faces that meet at a common vertex. Okay, so it can be any base. It doesn't have to be a triangle, but the faces of a pyramid are always triangles. Okay, so polyhedron with polygonal base. So square, it could be a square, it could be a rectangle, it could be a hexagon, a dodecagon, polygonal base with triangular faces, lateral faces, meeting at a common vertex. Okay, so here's like what we call a square pyramid. So a square pyramid has a square base, and then all its lateral faces are triangular. So instead of a prism where all the lateral faces are parallelograms, in a pyramid, all the lateral faces are a triangle. So this is an example of a pyramid. This would be an example of like a prism. It's not a rectangular prism. Right? So there's a prism. So there's a difference between a pyramid and a triangular prism. A triangular prism is a prism because it has two triangular bases. A pyramid is the only thing triangle about it are the sides. It doesn't have to have a triangular base. You could have a triangular pyramid, which has a triangle base, but it still has triangular lateral faces. Okay. So do you know what the plural for polyhedron is? Anyone know?
Polyhedrons.
No.
Polyhedri.
Close. Polyhedra.
Pretty much. I was gonna guess that.
Really?
Yeah.
It's not hydra. It's not hydra. It's polyhedra. Okay. So there's some more examples of classifying. I think you guys are good on that. So now here's the cool thing is you can determine how many edges or how many vertices, how many edges and how many faces if you're given the other two options. But for any polyhedron, here, let me show you this. Example 3, let's just look at example 3 together. Okay, so here's base. So let's see how this is still a pyramid here. It's a hexagonal pyramid, but it's still a pyramid. Here's a this is a pyramid on top, A, and then B is a triangular prism. Okay. All right, now look at this. Example 3, describing characteristics of a solid. So you need to be able to look at something and see how many edges, faces, and vertices there are. Okay, so we're going to classify the polyhedron in the diagram, assuming all the angles of each pentagon are congruent. Okay, so we could say a regular in there. We could say this is a regular pentagonal prism. Okay, so the figure has 2 parallel pentagonal bases. So we say it's a regular because the bases are what determine whether it's regular or not. Remember, regular means all the angles are the same and all the side lengths are the same. Okay. All right, so it's a regular pentagonal prism. And so the sides of the bases are all congruent and is given, so it is a regular prism. Since the lateral faces are not congruent to the pentagonal bases, it is not a regular polyhedron. Oh, that makes sense. So the sides are not congruent. So a regular polyhedron is a little different. You can still say it's a regular pentagonal prism, but you can't say it's a regular polyhedron. Polyhedron, you've probably seen that like a dice, like if you roll dice, that's a regular polyhedron because all the edges are the same length, okay? You've probably seen those dice where it's like a polyhedron, but it's like 5 sides. So have you seen those dice where it's like weird?
Like 20.
Yeah, so those are regular polyhedrons because all the side lengths are the same. All the angles are the same, okay? So you have to determine how many edges, how many vertices, and how many faces it has, okay? So it already has 2 because of the bases. But then each of those, since they're pentagonal bases, you're going to have 5 parallelograms going over the side. So there's 2 faces plus 5 more, so that's 7 faces, okay? And you have 15 edges. That makes sense because there's 5 around the sides, and then there's 5 on the top and the bottom, so 15 edges. And then vertices, there's just, in a prism, you just look at how many vertices there are on top and double it, so 10. So one diagonal is the segment BF. I don't know why they did that, but oh well. So a diagonal goes from vertice to vertice through the prism, I guess. Okay, now here's a cool thing. Anyone know how to pronounce this dude's name?
Euler's.
So if you...
Euler's. Euler's.
Anyone?
Euler. It's like Eugene, so it's like Euler's.
Euler.
Euler's. That's such a good movie.
Nope. I heard something close.
Euler's.
No.
Euler's.
Euler's.
Football team.
Wooler's. I don't watch Lions. Say it. That's the only Wellers.
This is pronounced Oilers.
What the? That's
So I was
terrible.
boy.
Yeah, but you just weren't confident in it, so you lost it. I was going to give you a free problem set.
That's horrible.
Oh, well.
Why would it be
I
pronounced like
told
that?
you Oilers.
I said I heard it. I think I heard it, but then you didn't repeat yourself.
I did. Okay.
No, I didn't.
We all told you. Mm-hmm. Sure it is.
That's not how it should be pronounced. That should be said. Like, think about Eugene. It's same for 2 letters.
Yeah, it's kind of a weird pronunciation, but he has a formula that works for every polyhedron. Okay, here's his formula for any polyhedron with B vertices, E edges, and F faces. So the number of vertices minus the number of edges plus the number of faces always equals 2. Okay, so if you are solving for one of these, you can either rearrange that equation or you can just plug in what you know and solve for what's left. Okay, so here's example 4. How many faces does a polyhedron with 12 vertices and 18 edges have? How many faces how many faces does a polyhedron
We're solving for F.
with 12 vertices, yep, vertices and 18 edges have?
Wait, I hate reiterating.
Okay, anyone know? Anyone got it?
Can you like?
Oh, 18. The 8.
No. That'll give you 22, not 2. Oh wait, let's see. Did I do it wrong?
No, it would be 8, wouldn't it?
Yeah, so 8 faces. Did you say 8?
Yeah.
Okay. Yeah, for some reason I thought they were looking for edges. So yeah, we're just going to plug in 12 for V. So we get 12 minus E for 18 for edges plus F equals 2. So let's see, that's negative 6 plus F equals 2. So what do you add to negative 6 to get, or you just add negative 6, add 6 to both sides? F equals 8. So 8 faces.
I thought it should be said that you and your brother should decide on a neutral way to solve formulas. I mean, to solve problems.
I mean, you could get E by itself first, but I just want to do math once instead of twice. Is that so wrong? Maybe you should tell him that. So, so we're solving for F. So we're going to put everything on the other side. So 2 minus V plus E. And now you have a nice confusing equation that you can solve
No, it's
that
not.
with.
It's 12 plus 18 minus 2 minus 2 plus 18.
All right. Okay. All right. Now, that's pretty much it for lesson 49. Let's move on to lesson 50. So actually, here's something interesting. Diamonds are cut to change them from rough stone into gemstone. The figure below shows 2 steps in cutting a particular diamond. And each of the other vertices is cut to the next steps. What is the number of faces, vertices, edges, and diamonds? Okay, so that's a cool little thing. You might have a problem like this on your next test, not this next test, but the one after. So we will review that once we get there. So, all right, moving on to lesson 50. Okay, lesson 50, we're going to talk about geometric mean, which is just another formula for you to know, which is okay. It's kind of like the normal mean, which is average, right, on steroids. So it's kind of taking this idea of an average up a level here. So this is how this concept starts. When an altitude is drawn from the vertex of a right triangle, 90-degree angle, to its hypotenuse, it splits the triangle into 2 right triangles that exhibit a useful relationship. Okay, so for example, here is a So here is a right triangle here. So when I'm drawing an altitude in a right triangle, here's what happens. This is theorem 50-1. The altitude is drawn to the hypotenuse of a right triangle. Then the two triangles formed are similar to each other and to the original triangle. If altitude is drawn to a right triangle's hypotenuse, then it forms two similar triangles and to the original triangle. So first of all, it forms two congruent triangles. Actually, no, this is just in this one, but you could draw it like this. You could draw a right triangle like this. Okay, so here's another right triangle. If I drew an altitude here, what it would look like? It would look like this. So do you see those three triangles that we drew? They all look like this. They all look like that original triangle. Here's a baby version of that original triangle, right? Here's the bigger version of that original triangle, just flipped upside down. And then the original triangle is the biggest one. Okay? So it forms three similar triangles. Okay, there is a proof if you want to look at that, but we are going to skip past that for now. Okay, so I'm going to do, this is example 2. I'm going to just redraw it here. So here's a right triangle. So if I want to draw, let's see here, the dimensions, I'm just going to say this is 5 units. I'm going to draw a altitude there. And then I'm going to give you these lengths. Let's say this is a 3, 4, 5 triangle. So if I'm given these lengths, that means I can find the dimensions of everything else. I can find this and I can find this. Figure it out. Since this is a 3, 4, 5 triangle, I could use that if I wanted to, but I'm going to set up some proportions. Okay, so they labeled it PQRS. So PQRS. I'm going to call that cursive S. Okay. So basically, look at these similar triangles here. If I took this little triangle here and I flipped it around and then turned it this way, that would be that triangle. If I took this triangle right here and I flipped it around and I turned it that way, and it would be that triangle. It's just similar, okay? So you have to figure out which side goes with which. All right? So for example, here are some ratios. SQ. SQ is right here. SQ is to, let's see, SR. SQ is to SR as, let's see, this side, which is the second longest side, is to the shortest side as what? Well, look at the big triangle. The second longest would be PQ. So PQ is to RQ. Or QR, and then which is PS to QS. And then if you look at this triangle, let's see. In this triangle, this is the shortest side. So PS, the medium side is PS. The short side is QS. Okay, so you can find the rest of them. So we do know what these guys are. We do know that SQ is 4. So 4 is to SR, which is 3. As PQ is to QR. Well, QR we already know is 5. So PQ is to 5. Okay. So let's see. How do you figure out what PQ is? Fish method, yeah. 20 divided by 3, which is 20 thirds, or 6.6 repeating. Okay. And then what about PS? Well, we know what QS. We know what QS is. So we can say 4 is to 3 as PS is to QS, which is 4. So that's 16 divided by 3, which is 5.3 repeating. Okay, so sometimes the means of a proportion are equal to one another. Okay, so the means of a proportion are equal to one another. So remember, there's like the extreme and then the means type of thing. We talked about the extreme and the means in a proportion, but here's what we're getting to, the geometric mean. So this is a special kind of proportion that can be used to find the geometric mean of two numbers. So the geometric mean for positive numbers of A and B is the positive number X, such that, okay, so if I had A over X and X over B, so see how these are the extremes and these are the means. In a proportion, the top left and the bottom right are the extreme numbers, and then the mean, the ones in the middle, are those. Now this time, the number in the middle is the same. So how do you find X? If you're just given A and B, you can find X. Do you know why? Because these cross products have to be the same. So X squared has to equal AB. So how do you find X? How do you solve for X? Yeah, so you have to get rid of that little 2. Opposite operation of squaring something is square rooting. So X equals the square root of AB. So you know how when you find the average or the mean of two numbers, how do you find the mean of two numbers? What do you do?
Add them together and then divide by 2.
Divide by 2, right. So you add the two numbers together, you add and then divide, right? So geometric mean is kind of like average on steroids. Instead of adding, you're going to do the next step up, which is multiply the two numbers. And instead of dividing, you're going to do the next step up, which is square rooting two numbers. So the geometric mean is when you multiply the two numbers and square root that, instead of adding the two numbers and dividing. Do you see how that's kind of like you take both operations to the next crazy level? So it's like the normal mean on steroids is the geometric mean. So that's easy. You don't have to worry about proportions or any of that garbage. You can find the geometric mean of two numbers by just multiplying them together and then taking the square root. Okay, so let's find the geometric mean of 3 and 12. Here's example 3. Find geometric mean, so I'm going to call it geomean, of 3 and 12. Does anyone have it already? What's the geometric mean of 3 and 12? Nope. How do you find the geometric mean of two numbers? What do you do? We just talked about it. Nope. You don't add them together and divide by 2. That's the normal mean. The geometric mean is different. How do you find the geometric mean of two numbers? Remember, it's the normal mean on steroids. Okay.
Square root it?
You don't square root it yet. Take notes. Write this down. To find the geometric mean, multiply two numbers, then square root. What's the geometric mean of 3 and 12?
Wait, so I got 7.5 and I square root that?
Because you got 7.5 because you found the normal mean of 3 and 12. You added the 2 and divided by 2. I want you to find the geometric mean. What?
Is it 3?
Nope,
Is it 6?
it is 6. How'd you get 6? What'd you do?
I times 3 and 12 and then I square rooted it.
Yeah, so you're one of those weird people who did what I told you to do. Nice job. So 3 times 12 is 36. Square root of 36? 6. Okay? Now you could do it. I mean, just do it. Follow these directions. 3 times 12 and then square root it. That's just a square root of 36, which is 6. Or you could set it up like a proportion. 3 and x equals x and 12. And then the fish method doesn't really work, but the cross products, that's where you get the fish method. The cross products have to be equal. So x squared equals 3 times 12. X times x equals 3 times 12. So x squared equals 36. So x has to be 6. Okay? All right. Here's some redemption. Find the geometric mean of, so this is 3a, example 3b. Find the GM of 2 and 9. Go. What's the geometric mean of 2 and 9? It's not 9.
Is it 3?
It's not 3.
7.
Is it 4?
Is it 7? 6. It's 6.
Let's follow the directions. How do you find the geometric mean of two numbers?
Hold on.
You multiply the two numbers and then you square root it.
Huh?
And so
No,
it would
what's
be
the
18. And square root 18, is it 9?
Oh, that's
No,
18
it's,
divided by
it's
2.
the- No, because
neither of
there's
them.
not a perfect square. It's not a perfect square,
Not a
right?
perfect
So you
square.
have to take the, what are the square roots that go into it? It's what? 9 and 2, obviously. And then from that, there you go, it's 3 to 2. So it's 3, whatever it's called.
So it's
Yeah.
Nice
radical
job.
3.
Nice job.
Right?
3 radical
3
2.
radical
Oh,
2.
3. Oh.
Okay, so
Wow,
you
it's hard to
see
be this
that
smart.
all of you should know that the answer is square root of 18. Does the square root of 18 make sense so far? Because you multiply 2 times 9, and then you take that answer and square root it. Square root of 18, which the first knee-jerk reaction is to divide it by 2 when you're finding the square root of something. Square root of 10 is not 5. The square root of 10 is the square root of 10.
It's
10 divided by 2 is 5.
5 radical 2.
No, it's just the square root of 10 because there's no perfect squares that live inside of 10. Okay? So square root of 18, everyone should get that far. You just do two things. You multiply, and then you take the square root, if you can. If you can't take the square root of something, then leave it alone. Unless there's something that can be reduced. So there is a 9 in there that you can take out, it becomes a 3. So if you get to square root of 18, you've done it right. You just need to clean up your answer. Okay? All right, let's do another one. What's the geometric mean of 25 and 4? What's the geometric mean of 25 and 4? Janae?
Wouldn't that just be 10?
10. Yes, because 25 times 4 is 100. Square root of 100 is 10. That was nice. Okay, what's the square root? What's the geometric mean? First of all, what's the normal mean of 2 and 3?
Wait, what's the question?
2.5.
2.5. Okay, the normal mean is just adding them and dividing
Yeah.
by 2. Now what's the geometric mean?
2 times 3 is 6.
Nope, not square root of 5.
2 times 3 is
Straight.
6. So 6 square rooted, it's 3 and 2. 2 rounded.
No, you can't do that. You can only take out, you only want to do that if there's a perfect square you can take out. It's just square root of 6.
Why can't you take out the 2 and 3? They're
Well,
both
but
perfect
2 is not a
squares.
square, and
Oh,
neither
no.
is 3. But you can
yeah.
take this 9 out because it's a square.
Yeah.
Okay? So it's just a square root of 6. Okay? So it does not seem like it's the normal mean on steroids because it's like you're not adding the 2, you're multiplying the 2. You're not dividing the answer by 2, you're square rooting it. Okay? That's crazy. All right, a couple corollaries. If the altitude is drawn to a hypotenuse of a right triangle, then the length of the altitude is the geometric mean. Okay, here's the corollary to this. Corollary of theorem 50-1. So corollary 50-1-1. We're going to say if this same if is there, then the length of the altitude, so this length right here, length of altitude, is the geometric mean of geometric mean between the segments of the hypotenuse. So let's see here. If this is the geometric mean of this, so this PS is actually, what is PS? 5 1/3. So 3 times 5 1/3 is actually 16. So 3 times 5 1/3 is 16. Square root 16, you get 4. So this altitude is going to be the geometric mean of these two lengths. Okay? Of segments of hypotenuse. So not the hypotenuse, but the two segments of the hypotenuse, the segments that were formed when you drew the altitude. Okay? So let's do an example there. What if let's see here. If this was
5 and 2. 6 and 2.
let's try
7 and 3. 7
trying to
and 3.
think of one that's easier.
5 and 2. 5 and 3.
0 and 0.
This is drawn poorly, but what would this altitude be? Let me draw it better.
18. I mean 8.
So if this was 4 and 16, what is that altitude?
It would be 8.
How'd you get 8?
I just mathed.
What's your math?
64
plus-
squared.
I was gonna say, I don't know. It's just multiply and then square.
Multiply and then square root. 4 times 16 is 64. What's the square root of 64?
8.
8. So this is just the square root of 4 times 16. So that altitude is going to be the geometric mean of the two segments that were formed from that hypotenuse. Okay? Corollary 50-1-2 is a little confusing, so I'll let you write it down if you like, but don't stress too much about this. Here's corollary 50-1-2. Now try to picture this. If the altitude is drawn to the hypotenuse of a right triangle, same scenario that we're in, then the length of a leg is the geometric mean between the hypotenuse and the segment of the hypotenuse that is closer to that leg. What? So that means,
So it would be the hypotenuse of the 4.
yeah, so if we come back to this example here, then the length of a leg, like one of these lengths, like this one, 5, is the geometric mean between the hypotenuse and basically the other leg, and the segment of the hypotenuse that is closer to that leg. Okay, so it'd basically be the geometric mean of the hypotenuse, which is, what is that, 8 1/3 and 3. Okay, what's 8 1/3? What's the geometric mean of 8 1/3 and 3? So that's 25. Square root of 25 is 5. Okay, that's kind of a confusing formula that you probably won't ever have to use. So don't stress about that. But that is a nice little shortcut. Those corollaries are taking the truth of this, and since they're proportional, they're similar triangles, you don't have to draw all the triangles separately and do all that. You could if you wanted to. You could just find the geometric mean of the two hypotenuse segments to find the length of the altitude. Or you can find the length of basically that leg by finding the geometric mean of the hypotenuse and the segment of the hypotenuse that is closest to that leg. So if this leg was something else, and to find that, I would find the geometric mean of 8 1/3 and 5 1/3. That would be the geometric mean. That's a crazy decimal right there. Okay. So you'll get some, let's just do this example together. So let's see if we can find some missing things here. So first of all, let's find the length of y. How do you find y? What did we say?
Geometric mean of 3.
Yeah, the geometric mean of 3 4/3. What's 3 times 4/3? Cancel the 3's. What do you get? 4. What's the square root of 4?
No. It's
2, right?
2.
Okay. So 3 times 4/3 is 4. Square root of 4 is 2. So y equals 2. Okay. Now what about, let's find the length of TU.
You could write down 0.
So the length of T, yeah, you could use the Pythagorean theorem. That would be a pain in the butt, but you could, because you have y now and you have 4/3. So you could find it, or you could just find the geometric mean using corollary 51(2). You could find the geometric mean of 3 plus 4/3, which is 4 1/3, and 4/3. So if I add 4 1/3 and 1 1/3, I get 5 2/3, and then I square root that. That would give me TU. Okay. All right, so let's try one that's a little easier. So this time we're looking for A and B. Okay. Anyone know how to find A using corollary 50-1-2? Anyone know?
So, wait.
So corollary 50-1-2 says that 3 is the geometric mean of 5 plus A, but you don't know what A is. So let's see if we can go back here. First of all, that's a 3, 4, 5 triangle. So to figure that out, let's see here, the geometric mean. So we could find the altitude first and do it geometric way, or what they did. Yeah, so they're using 50-1-2. So 3 or 4, let's see here. Well, let's see what they did. So 3, yeah, 3 is the geometric mean, so of A and 5. Okay, so basically you'd have 5 times a square rooted would equal 3, or you could set it up like this. See how 3 is a geometric mean because they're both the same, and then you have a and 5. So you fish that out, you get 9/4. You fish that out, and you get 16/5. Or 9/5 and 16/5, sorry. Okay. That's about it.
Black math, give me some math and I'll give you some flack. Black math.